Today, we're diving into a fascinating study that explores the performance of language models when assessing relevant information within input context. Get ready to uncover some intriguing findings. One notable observation from the study is that language model performance tends to be highest when relevant information occurs at the beginning or end of the input text. However, as models are required to access relevant information in the middle of a long context, their performance significantly degrades. Furthermore, as the input context grows longer, performance experiences a substantial decrease. Language models are predominantly implemented using transformers, which struggle to handle long sequences efficiently due to the quadratic complexity of self-attention with respect to input sequence length. Models are typically trained with relatively small context windows. While recent hardware and algorithm improvements have led to larger context windows, it remains unclear how these models utilize their input context when performing downstream tasks. The study investigates this phenomenon using a range of state-of-the-art open models such as MPT-30B, InstructSet, LongChat 13B, 16K token, as well as closed models like OpenAI's GPT 3.5 Turbo and Anthropic's Claude. The research focuses on settings that require accessing and utilizing information within an input context, including multi-document question answering and key value retrieval. In the multi-document question answering experiments, the models receive a question to answer and a set of K documents, where one document contains the answer while the rest serve as distractors. Varying the number of input documents between 10, 20, and 30, the study reveals a distinct U-shaped curve in model performance. Models demonstrate significantly better performance when identifying and utilizing relevant information at the very beginning or very end of the context. For instance, GPT 3.5's turbo performance on multi-document QA can decrease by more than 20% in the 20 and 30 document settings. Its performance dips lower than its closed book performance, which refers to performance without any input documents. The study also examines a synthetic key value retrieval task, where the models receive a serialized JSON object with K key value pairs. The goal is to retrieve the value associated with a specific key with varying numbers of key value pairs between 75, 140, and 300. The results demonstrate similar trends. Once again, a U-shaped performance curve emerges, indicating that model performance is lowest when the key value pairs are located in the middle of the input context. To gain insights into the role of model architecture, the study conducts preliminary investigations comparing decoder-only models to encoder-decoder models like FLAN UL2 and FLAN T5XXL. The findings suggest that encoder-decoder models tend to make better use of their context windows due to the bidirectional encoder, allowing for processing each document in the context of future documents. This enhances the estimation of relative importance between documents. It's worth noting that decoder-only models cannot attend to query tokens, as the query only appears at the end of the prompt. They can only attend to prior tokens. On the other hand, encoder-decoder models use a bidirectional encoder to contextualize input contexts, making them more robust to changes in the position of relevant information. Introducing RoboCat, an innovative self-improving foundation agent for vision-based robotic manipulation. RoboCat is a state-of-the-art large transformer sequence model that has been trained on a vast dataset of diverse and precise vision-based tasks. With the advent of high-capacity models like the Transformer, they have witnessed incredible advancements in multitask learning for language and vision. Building on this progress, RoboCat was trained on an extensive dataset that encompassed a wide range of vision-based tasks. These tasks were performed using various robotic embodiments, each with different degrees of freedom, observation, and action specifications, and control frequencies. Each task is defined by its accountability infinite set of valid start and end states. task success is evaluated by checking if the final state aligns with a set of valid end states. To introduce diversity into the dataset, they employ multiple simulated and real embodiments and adapted different approaches to data generation. These included RL-trained expert trajectories, human teleoperation demonstrations, as well as self-generated data by RoboCat itself. The authors' work involved the use of 36 real robots, 15 panda arms, 17 soya arms, and 4 kuka arms. Data generation comprised 3 types. Specialist RL agent data primarily employed in simulation. 2 was human teleoperated expert data predominantly used for real-world tasks. And 3, generated data. The key distinction between the RL agent data and teleoperated data lies in the smoothness and efficiency of the trajectories, with teleoperated data often including pauses. The self-generated data was collected through extensive evaluations. Whenever a new version of RoboCat became available, the data collected during these evaluations were then saved and reused for subsequent RoboCat training iterations. The self-generated data closely resembles the behaviors observed during teleoperation, as it derived from RoboCat agents fine-tuned on teleoperated expert data. RoboCat demonstrates superior performance across a wide range of training tasks, outperforming equivalent single-task baseline agents trained on the same data for each task. To establish this, they compared RoboCat with the best-performing visual foundation model-based agents, chosen from a pool of 59 strong baselines. Notably, in the real world, where data is limited compared to simulation, RoboCat's multitask joint training approach proves highly advantageous, significantly surpassing the baselines. Unlike high-capacity pre-trained vision foundation models, agents trained for single tasks, RoboCat effectively leverages the extensive training data available to it. The author's experiments demonstrate that RoboCat, with its ability to learn from heterogeneous data using visual goals, can perform a wide array of tasks across multiple robotic embodiments. Moreover, it can quickly adapt to unseen tasks, new object sets, and even new embodiments, all with a limited number of demonstrations. This self-improvement process, involving fine-tuning and self-generating additional data, proved to be significantly more effective than relying solely on demonstrations during generalist training. Most remarkably, the author's experiments revealed that the cost of acquiring new skills is dramatically lower when using RoboCat compared to single-task baselines, even when those baselines are built on visual foundation models.